Time has always been humanity's most mysterious companion, woven into every culture's deepest stories and philosophies, from ancient Egyptian priests tracking the floods of the Nile to Buddhist monks contemplating the eternal wheel of existence, from Mayan astronomers calculating vast cycles of creation to Aboriginal dreamtime stories that blur past and future into one eternal present. Every civilization has grappled with time's enigmatic nature, trying to understand this invisible river that carries us all forward into tomorrow. Tonight, we're going to journey through all of it, every moment that has ever been, from the very first instant when time itself began, through the long, patient ages of cosmic evolution, through the birth of stars and planets, through the emergence of life and consciousness, right up to this very moment, as you listen to these words and then beyond, into the deep future that awaits. This is the complete story of time, told in a way that will gently carry you into peaceful sleep, a bedtime story that spans nearly 14 billion years. Close your eyes and let yourself sink into comfort as we begin at the very beginning, at a moment so strange and powerful that it gave birth to everything we know. We're going back now, back through all the years, all the centuries, all the eons, back to a time before there were any clocks to measure moments, before there were any stars to mark the passage of days, before there was even space for anything to exist in. We're going back to the first moment of time itself. 13,800,000,000 years ago, something extraordinary happened. In a space smaller than the smallest particle you could imagine, smaller than an atom, smaller than the components that make up atoms, smaller even than the vibrating strings that might lie at the heart of all reality, everything that would ever exist was compressed into a point of infinite density and infinite temperature. This wasn't just matter and energy packed together, it was space itself, curled up so tightly that there was no room for anything to move, no distance between any 2 points. And then, in a moment that defines the word moment itself, it began. The Big Bang wasn't an explosion in space, it was an explosion of space. Imagine the universe not as something expanding into emptiness, but as space itself stretching, creating room where none existed before. In that first incomprehensibly brief instant, lasting just 10 to the negative 43 seconds, a period so short that we call it Planck time, after the physicist Max Planck, who first conceived of these fundamental units, the universe underwent a transformation so profound that all the laws of physics, as we understand them, were being written into existence. The temperature in this newborn universe was 10 to the 32nd power Kelvin, a number so vast that it loses meaning to our everyday understanding. This wasn't heat as we know it, with molecules vibrating and atoms dancing. This was pure energy, so intense that matter and energy were interchangeable, flickering back and forth between states in a cosmic dance of creation and annihilation. Every particle that came into being instantly met its antiparticle twin and vanished back into pure energy, only for that energy to split again into new particle pairs, over and over, in an endless cycle of birth and death, happening billions of times in spaces smaller than anything we can measure. As the universe expanded, doubling in size every 10 to the negative 34 seconds during a period called cosmic inflation, something remarkable was happening to the fundamental forces that govern all existence. In our daily lives, we experience 4 fundamental forces as completely separate phenomena. Gravity keeps our feet on the ground and planets in their orbits. Electromagnetism gives us light and radio waves and the chemistry that makes life possible. The strong nuclear force holds atomic nuclei together, while the weak nuclear force governs certain types of radioactive decay. But in these first moments, these weren't 4 forces at all. They were one unified superforce, a single principle governing all interactions in the universe. As the universe cooled, dropping from those unimaginable temperatures toward merely trillions of degrees, this superforce began to split apart like ice crystals, forming in cooling water. First, gravity peeled away from the other three, becoming its own distinct force at around 10 to the negative 43 seconds after the beginning. The universe was still so small at this point that you could have held it in your hand if your hand could somehow exist in those conditions, though it was expanding so rapidly that within another fraction of a second it would be larger than our entire solar system is today. The cosmic inflation that drove this expansion was unlike anything that happens in our universe today. Space itself was stretching faster than the speed of light, which might seem impossible given that nothing can travel faster than light. But this wasn't movement through space. It was the expansion of space itself. Every point in the universe was rushing away from every other point, not because they were moving, but because new space was being created between them. In less time than it takes light to cross a proton, the universe expanded by a factor of at least 10 to the 26, transforming from subatomic to astronomical scales. This inflation solved several profound mysteries about our universe. Why does the universe look essentially the same in all directions when we observe it today? Because all those regions were once in contact, able to exchange information and reach equilibrium before inflation drove them apart. Why is space so geometrically flat, neither curved inward like a sphere nor outward like a saddle? Because inflation stretched out any initial curvature until it became imperceptible, like how the surface of an enormous balloon appears flat to someone standing on it. And why don't we see magnetic monopoles and other exotic particles that theories predict should have formed in the early universe? Because inflation diluted them to such an extent that there might be only one in our entire observable universe. As inflation ended, around 10 to the negative 32 seconds after the beginning, the energy that had been driving this exponential expansion didn't simply disappear. Instead, it transformed, decaying into a hot soup of particles and radiation that filled the now vastly larger universe. This reheating, as cosmologists call it, brought the temperature back up to around 10 to the 27 Kelvin, still incomprehensibly hot, but now in a universe with room to evolve. The next phase of the universe's story unfolded over what seems like an eternity compared to those first fractions of a second, though it was still just the briefest beginning of cosmic history. Between 10 to the negative 12 and 10 to the negative 6 seconds after the Big Bang, the electromagnetic and weak nuclear forces, which had been unified as the electroweak force, finally separated into the distinct forces we observe today. The universe was filled with a plasma of quarks and gluons, the fundamental particles that would eventually combine to form protons and neutrons, but it was still far too hot for them to stick together. This quark-gluon plasma was unlike any state of matter that exists naturally in our universe today. The quarks, which come in 6 varieties whimsically named up, down, charm, strange, top and bottom, were moving freely through space, unconfined by the strong force that would later lock them together. Gluons, the particles that carry the strong force, were zipping between quarks but couldn't yet bind them into stable combinations. The density of this plasma was incredible, roughly 10 to the 18th kilograms per cubic meter, about the same as an atomic nucleus but filling all of space. As the universe continued expanding and cooling, a critical transition occurred at about 10 to the negative 6 seconds, when the temperature dropped below 2 trillion Kelvin. Suddenly quarks could no longer remain free. The strong force pulled them together into combinations of 3 quarks, forming protons and neutrons, or combinations of a quark and an antiquark, forming mesons. This phase transition, called the QCD phase transition, after quantum chromodynamics, the theory that describes the strong force, happened everywhere in the universe simultaneously, transforming the entire cosmos from a soup of free quarks into a gas of composite particles. But the universe's particle population was still in flux. Protons and neutrons were constantly transforming into each other through interactions mediated by W bosons, carriers of the weak nuclear force. A proton would emit a W plus boson and become a neutron, while a neutron would emit a W minus boson and become a proton. At these extreme temperatures, these transformations happened at equal rates, maintaining a balance between the two types of particles. This balance would prove crucial for the future of the universe, as both protons and neutrons would be needed to build the first atomic nuclei. Meanwhile, the universe was filled with a brilliant light. Though calling it light doesn't quite capture its intensity, photons were constantly being created and destroyed, interacting with all the charged particles that filled space. The energy density of this radiation was so extreme that photons were continuously creating particle-antiparticle pairs through a process called pair production, where a high-energy photon transforms into, say, an electron and a positron, its antimatter counterpart. These pairs would then annihilate each other almost immediately, creating new photons which would create new pairs in an endless cycle of creation and destruction. At 1 second after the Big Bang, a crucial milestone was reached. The temperature had dropped to about 10 billion Kelvin, still 700 times hotter than the centre of our Sun today, but cool enough that a significant change occurred in the balance between matter and radiation. Neutrinos, those ghostly particles that barely interact with anything, decoupled from the rest of the matter in the universe. Up until this point, even neutrinos, which can pass through light years of lead without interacting, were being constantly scattered by the intense density of particles. But now the universe had expanded enough that neutrinos could travel freely through space, creating what we call the cosmic neutrino background, a sea of ancient neutrinos that still fills the universe today, though they're so weakly interacting that we've never directly detected them. The decoupling of neutrinos had a profound effect on the ratio of protons to neutrons. Without neutrino interactions to maintain equilibrium, neutrons began to decay into protons through beta decay, where a neutron transforms into a proton, an electron, and an antineutrino. Free neutrons are unstable, with a half-life of about 10 minutes, and without the reactions that had been converting protons back into neutrons at high temperatures, the neutron population began to dwindle. By the time the universe was about 10 seconds old, there were only about 2 neutrons for every 14 protons, a ratio that would determine the composition of all the ordinary matter in the universe. Now we enter what cosmologists call the era of Big Bang nucleosynthesis, a period lasting from about 10 seconds to 20 minutes after the beginning, during which the first atomic nuclei were forged. The temperature had dropped to about 3 billion Kelvin, cool enough for protons and neutrons to stick together when they collided, but still hot enough for nuclear fusion reactions to occur. The process began simply, with a proton and neutron combining to form deuterium, an isotope of hydrogen with 1 proton and 1 neutron in its nucleus. But there was a bottleneck in this process, something physicists call the deuterium bottleneck. Deuterium nuclei are relatively fragile, and at temperatures above 1 billion Kelvin, they're destroyed by high-energy photons as quickly as they form. The universe had to cool below this critical temperature before deuterium could survive long enough to fuse into heavier elements. This didn't happen until the universe was about 2 minutes old, by which time more neutrons had decayed, leaving only about 1 neutron for every 7 protons. Once deuterium could survive, nuclear fusion proceeded rapidly. Deuterium nuclei collided with protons to form helium-3, or with other deuterium nuclei to form tritium or helium-3 plus a neutron. These light nuclei then fused further, with almost all pathways leading to helium-4, the stable isotope of helium with 2 protons and 2 neutrons. The process was remarkably efficient. Within just a few minutes, essentially all the remaining neutrons were locked up in helium-4 nuclei, with trace amounts of deuterium, helium-3, and lithium-7 left over. The final abundances were set by that ratio of neutrons to protons. About 75% of the ordinary matter in the universe remained as single protons, which are just hydrogen nuclei, while 25% formed helium-4. Only about 0.01% formed deuterium, with even smaller traces of other light elements. These proportions, predicted by Big Bang nucleosynthesis theory and confirmed by observations of the oldest stars and gas clouds, provide some of our strongest evidence for the Big Bang model of cosmology. By 20 minutes after the Big Bang, the universe had cooled below 600 million Kelvin, too cool for any further nuclear fusion to occur. The cosmic kitchen had closed, having cooked up only the lightest elements. All the heavier elements that make up our world, the carbon in our bodies, the oxygen we breathe, the iron in our blood, would have to wait billions of years to be forged in the hearts of stars. But for now, the universe had its first atoms, or rather, its first atomic nuclei, as it was still far too hot for electrons to settle into orbits around them. The universe at this point was a brilliant opaque plasma. Photons couldn't travel far without scattering off free electrons, making the universe look like the inside of a star, glowing with its own light but impossible to see through. The temperature was still measured in millions of degrees, and space was filled with a bath of radiation, so intense that matter was almost an afterthought, contributing less than 1% of the total energy density. This was the radiation-dominated era, a time when light itself was the primary constituent of the universe. As the universe expanded over the following thousands of years, an important transition occurred. The energy density of radiation decreases faster than the energy density of matter as space expands, because not only does radiation get diluted as space grows, but each photon also loses energy, its wavelength stretching with the expansion of space. Matter, on the other hand, only gets diluted. Around 47,000 years after the Big Bang, these two effects balanced out, and matter began to dominate over radiation for the first time. The universe was entering the matter-dominated era that continues to this day. But the universe was still opaque, still a glowing plasma that no light could penetrate. This would remain true for hundreds of thousands of years, a period cosmologists call the photon epoch or the plasma epoch. During this time, the universe was slowly cooling, slowly expanding, slowly evolving toward a state where atoms could finally form. The temperature dropped from millions to thousands of degrees, and the brilliant white glow of the cosmic plasma shifted toward orange and then deep red, like a cooling ember in a dying fire. Throughout this era, gravity was beginning its patient work. Although the universe appeared remarkably uniform, there were tiny variations in density, regions where matter was slightly more or less concentrated than average. These variations, imprinted during cosmic inflation and visible today in the cosmic microwave background, were the seeds of all future structure in the universe. In denser regions, gravity pulled matter together ever so slightly, while less dense regions became ever emptier. But as long as the universe remained a plasma, radiation pressure resisted gravity's pull, setting up acoustic oscillations, sound waves that rippled through the cosmic plasma on scales of hundreds of thousands of light years. These cosmic sound waves were nothing like sound as we experience it. They were compressions and rarefactions in the plasma that took hundreds of thousands of years to complete a single oscillation. Regions would compress, heating up and glowing brighter, then expand, cooling and dimming in a cosmic rhythm that filled the entire universe. The pattern of these oscillations, frozen in place when the universe finally became transparent, would become one of our most powerful tools for understanding the cosmos, encoded in the tiny temperature variations of the cosmic microwave background radiation. As we approach 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, roughly half the temperature of the sun's surface today. At this temperature, a momentous change was about to occur. Electrons, which had been flying freely through space since the beginning, were finally moving slowly enough to be captured by atomic nuclei. When an electron encountered a proton, it could now settle into an orbit around it, forming the first true atom of hydrogen. When an electron met a helium nucleus, it would begin the process of forming a helium atom, though helium, requiring 2 electrons, would take a bit longer to become fully neutral. This process, called recombination, though it was really combination happening for the first time, transformed the universe in a geological instant. Within just a few thousand years, essentially all the free electrons in the universe had been captured by nuclei. The cosmic plasma that had filled space since the beginning became a gas of neutral atoms. And with the free electrons gone, photons could suddenly travel unimpeded through space. The universe, which had been opaque since its birth, became transparent. The moment of recombination released the oldest light we can observe today, the cosmic microwave background radiation. This light has been travelling through space ever since, stretched by the expansion of the universe from visible light to microwave radiation, cooling from 3,000 Kelvin to just 2.7 Kelvin today. When we detect this radiation with our telescopes, we're literally seeing the universe as it was 380,000 years after the Big Bang, observing the moment when atoms first formed and space became transparent. It's the baby picture of our universe, showing us the tiny variations in density that would grow into galaxies and clusters of galaxies over billions of years. With recombination complete, the universe entered what we call the cosmic dark ages. The name is apt, for this was a time when the universe was truly dark. The cosmic microwave background radiation was redshifting toward infrared wavelengths invisible to the human eye, and there were not yet any stars to produce new light. Space was filled with clouds of hydrogen and helium gas, dark and cold, slowly falling together under gravity's patient pull. For millions of years, perhaps as many as 100 million years, the universe remained in this state. A vast dark expanse with no sources of light except the fading glow of the Big Bang itself. But in the darkness, something remarkable was happening. Gravity was sculpting the universe on the grandest scales. The tiny density variations from the early universe were growing, amplified by billions of years of gravitational attraction. Dark matter, that mysterious substance that interacts only through gravity and makes up 85% of all matter, was forming vast halos, invisible scaffolding around which ordinary matter would collect. These dark matter halos grew through hierarchical merging, small halos combining to form larger ones, creating a cosmic web of filaments and voids that would define the large-scale structure of the universe. Within the densest dark matter, halos, ordinary matter, was collecting too, forming clouds of hydrogen and helium gas that grew denser and denser as gravity pulled them together. These clouds were enormous, containing the mass of millions or billions of suns, but they were still just gas, cold and dark, in the vastness of space. As they contracted, however, something began to change. The gravitational potential energy of the falling gas was converted to kinetic energy, causing the gas to heat up. The clouds began to fragment, breaking into smaller and smaller pieces as different regions collapsed at different rates. Deep within the densest fragments, the temperature and pressure were rising dramatically. When the core of a collapsing gas cloud reached about 2000 Kelvin, hydrogen molecules began to break apart into individual atoms. This actually accelerated the collapse, because molecular hydrogen had been radiating away heat, providing a kind of pressure that resisted gravity. Without this cooling, the gas clouds would have remained too hot to collapse further. But with the molecules destroyed, the gas could no longer cool efficiently, and the collapse proceeded even faster. The cores of these fragments continued to heat up as they collapsed, reaching 10,000, then 100,000, then 1,000,000 Kelvin. At around 10 million Kelvin, something extraordinary happened. The hydrogen nuclei were moving so fast that when they collided, they could overcome their electrical repulsion and get close enough for the strong nuclear force to take over. Nuclear fusion began, hydrogen nuclei combining to form helium and releasing enormous amounts of energy in the process. A star was born. The first stars in the universe were monsters unlike anything that exists today. Without heavy elements to help cool the collapsing gas clouds, only the most massive fragments could collapse all the way to stellar ignition. These first stars, which astronomers call population 3 stars, were typically hundreds of times more massive than our Sun. They burned with a fierce blue-white light, surface temperatures of 50,000 Kelvin or more, making them tens of thousands of times more luminous than the Sun. Their light began to fill the darkness, ending the cosmic dark ages and beginning the era of cosmic dawn. But these massive stars lived fast and died young. The more massive a star, the more rapidly it burns through its nuclear fuel. While our Sun will shine for 10 billion years, these first giants exhausted their hydrogen fuel in just a few million years. As they ran out of hydrogen in their cores, they began fusing helium into carbon, then carbon into oxygen, neon, and silicon, building up the periodic table element by element in their nuclear furnaces. The process continued, each new phase of fusion lasting a shorter time than the last, until iron began to accumulate in the stellar core. Iron is the end of the line for fusion in stars. Fusing iron into heavier elements doesn't release energy, it requires energy input. Without the outward pressure of fusion to support them against gravity, the cores of these massive stars collapsed catastrophically. In less than a second, the core would compress to nuclear densities, then rebound in a tremendous explosion, a supernova that could outshine an entire galaxy. These first supernovae were especially powerful, as the massive stars that produced them had such deep gravitational wells that the collapse released enormous amounts of energy. In the extreme conditions of these explosions, elements heavier than iron were forged through rapid neutron capture, creating gold, uranium, and all the other heavy elements that couldn't be made through normal stellar fusion. The explosions scattered these newly minted elements into space, enriching the surrounding gas clouds with the first heavy elements the universe had ever seen. Some of these first stars were so massive that they collapsed directly into black holes without exploding, creating the first black holes from stellar collapse, cosmic monsters that would grow over billions of years into the supermassive black holes we find at the centres of galaxies today. The light from these first stars had another profound effect on the universe. Their intense ultraviolet radiation began to ionize the neutral hydrogen gas that filled space, stripping electrons from hydrogen atoms and creating bubbles of ionized gas around each star. This process, called reionization, would eventually transform the entire universe, converting all the neutral gas between galaxies back into a plasma, though a much more diffuse plasma than existed before recombination. The process took hundreds of millions of years, with bubbles of ionized gas growing and merging until, by about 1 billion years after the Big Bang, the entire intergalactic medium was ionized. As the first stars lived and died, enriching space with heavy elements, a new generation of stars began to form. These population 2 stars were smaller than the first giants, because the presence of heavy elements, even in tiny amounts, made the gas clouds cool more efficiently, allowing smaller fragments to collapse into stars. These stars were more like the stars we see today, including many that were small enough to still be shining billions of years later. We can observe some of these ancient stars in our own galaxy, cosmic fossils that formed when the universe was less than 1 billion years old. The universe was also beginning to form larger structures. The first galaxies were assembling through the merger of smaller protogalaxies, collections of stars and gas clouds bound together by gravity within their dark matter halos. These early galaxies were small and irregular, nothing like the grand spirals and massive ellipticals we see today. They were chaotic places with intense star formation triggered by the constant infall of fresh gas and frequent collisions with other small galaxies. The rate of star formation in the early universe was prodigious, 10 or even 100 times higher than today, as galaxies converted their abundant gas supplies into new stars. At the centers of these growing galaxies, supermassive black holes were beginning to form. The exact mechanism is still debated among astronomers. Perhaps they grew from the remnants of the first stars, black holes of 100 solar masses that accumulated matter over millions of years. Or perhaps they formed directly from the collapse of massive gas clouds, creating black holes of 10,000 solar masses or more from the start. However they began, these black holes grew rapidly by swallowing gas and even entire stars that ventured too close, eventually reaching millions or billions of solar masses. As matter fell into these growing black holes, it formed accretion disks, spiraling whirlpools of superheated gas that glowed with incredible intensity. The energy released by matter falling into supermassive black holes powered quasars, the brightest persistent sources of light in the universe. A single quasar could outshine all the stars in its host galaxy combined, visible from billions of light years away. These cosmic lighthouses helped reionize the universe and regulated star formation in their host galaxies. Their intense radiation and jets of matter blown outward at near light speed heating and dispersing the gas that would otherwise form new stars. The cosmic web was becoming more defined during this era. Galaxies weren't distributed randomly through space but followed the underlying dark matter distribution, forming long filaments with clusters at the intersections and vast voids in between. Matter flowed along these cosmic highways, with galaxies streaming along filaments toward the growing clusters. When galaxies met, they sometimes merged in spectacular collisions that took hundreds of millions of years to complete, their stars passing through each other while their gas clouds collided and triggered bursts of new star formation. By 2 billion years after the Big Bang, the universe was beginning to look more familiar. Large galaxies had formed, including the first spiral galaxies with their distinctive rotating disks and spiral arms. The rate of star formation was beginning to decline from its early peak as galaxies used up their gas supplies, and feedback from stars and black holes heated the remaining gas, making it harder to form new stars. The chemical enrichment of the universe continued as each generation of stars produced and dispersed more heavy elements, gradually increasing the metallicity of galaxies. Around this time, something subtle but profound was happening to the expansion of the universe itself. For the first several billion years, the expansion had been slowing down, decelerated by the gravitational attraction of all the matter in the universe. But as the universe expanded and matter became more dilute, another component began to dominate: dark energy. This mysterious force, which acts like a kind of anti-gravity, had been present all along, but only became dominant when the universe had expanded enough that matter's gravitational influence weakened. About 5 billion years after the Big Bang, dark energy overcame matter's gravity, and the expansion of the universe began to accelerate. 9 billion years after the Big Bang, in a spiral arm of a relatively ordinary galaxy that had formed from the merger of several smaller galaxies, a cloud of gas and dust began to collapse. This cloud had been enriched by generations of stars that had lived and died, seeding it with heavy elements like carbon, oxygen, silicon, and iron. As the cloud collapsed, it began to rotate faster, conservation of angular momentum causing it to spin up like a figure skater pulling in their arms. The cloud flattened into a disk, with most of the mass collecting at the centre, while smaller condensations formed throughout the disk. At the centre of this collapsing cloud, temperatures and pressures rose until hydrogen fusion ignited, giving birth to our Sun. The Sun was a relatively ordinary star, a yellow dwarf that would burn steadily for billions of years. Around it, in the swirling disk of gas and dust, smaller objects were forming. Close to the Sun, where temperatures were high, only rocky materials could condense, forming the terrestrial planets Mercury, Venus, Earth, and Mars. Farther out, where it was cold enough for water and other volatiles to freeze, the gas giants Jupiter and Saturn grew massive enough to capture hydrogen and helium from the disk, while Uranus and Neptune formed as ice giants in the outer reaches. The early solar system was a chaotic place. Planetary embryos, objects ranging from moon-sized to Mars-sized, orbited the Sun in various orbits, occasionally colliding and merging to form larger bodies. The process was violent, with impacts releasing enough energy to melt entire planets. Earth itself formed through this process of accretion, growing from dust grains to pebbles to boulders to planetesimals to planetary embryos, finally reaching its current size after about 30 to 50 million years of growth. During this early period, Earth suffered a catastrophic collision with a Mars-sized object that scientists call Theia. The impact was so violent that it melted both bodies, throwing enormous amounts of debris into orbit around Earth. This debris, consisting mostly of material from the mantles of both bodies, eventually coalesced to form the Moon. The Moon was much closer to Earth initially, perhaps only 20,000 kilometres away, compared to 380,000 kilometres today, and the Earth's day was only 5 hours long, spinning rapidly from the angular momentum added by the impact. The young Earth was a hellish place, its surface covered in magma oceans from the heat of accretion and radioactive decay. The atmosphere consisted mainly of hydrogen and helium captured from the solar nebula, but these light gases were quickly lost to space, stripped away by the solar wind from our young, active Sun. Volcanic activity was intense, fed by the heat of the planet's formation and the higher rate of radioactive decay from short-lived isotopes that have since decayed away. The surface was constantly bombarded by asteroids and comets, the leftover debris from planet formation. As Earth cooled, a new atmosphere formed from volcanic outgassing, consisting mainly of water vapour, carbon dioxide, nitrogen, and sulfur compounds. This atmosphere was nothing like the one we breathe today, with essentially no free oxygen and a surface pressure, perhaps tens or even hundreds of times higher than present. The greenhouse effect from all the carbon dioxide and water vapour kept the surface warm, despite the Sun being about 30% dimmer than it is today, a phenomenon known as the faint young Sun paradox. When the surface temperature finally dropped below the boiling point of water, rain began to fall. And what rain it was! For perhaps millions of years, torrential downpours stripped water vapour from the atmosphere, creating the first oceans. These early oceans were probably much deeper than today's, as there were no continents yet, just a global ocean dotted with volcanic islands. The water was likely greenish from dissolved iron and other minerals, under a thick, hazy atmosphere that blocked most sunlight from reaching the surface. The formation of oceans fundamentally changed Earth's geology. Water lubricated the movement of crustal plates, enabling plate tectonics to begin. Subduction zones formed where dense oceanic crust sank beneath lighter material, recycling crustal material and volatile compounds back into the mantle. This process would prove crucial for maintaining Earth's habitability over billions of years, regulating the carbon cycle and maintaining a stable climate despite changes in solar luminosity. Life may have emerged surprisingly early in Earth's history, perhaps as soon as the oceans formed, or possibly even earlier, in warm little ponds on volcanic islands. The exact mechanism remains one of science's greatest mysteries, but somehow, in the chemical soup of the early Earth, molecules began to replicate themselves. These weren't living things as we would recognize them, just chemical systems that could make copies of themselves imperfectly, allowing for variation and evolution. Perhaps it started with RNA molecules that could both store information and catalyze chemical reactions, a simpler precursor to the DNA protein world that all life uses today. These early replicators faced enormous challenges. The young Earth was still being bombarded by asteroids and comets in what we call the Late Heavy Bombardment, a period around 4 billion years ago when the migration of the giant planets disturbed asteroids in the outer solar system, sending them raining down on the inner planets. Some of these impacts were large enough to boil away the upper layers of the oceans, sterilizing much of the planet's surface. Life may have started and been wiped out multiple times before finally taking permanent hold. The first true living organisms were probably something like modern bacteria or archaea, single-celled organisms without a nucleus, getting energy from chemical reactions involving hydrogen, sulfur, iron, and other elements abundant in the early Earth. They lived in extreme environments that would be instantly lethal to most modern life. Near volcanic vents on the ocean floor, where superheated water carried dissolved minerals up from the mantle, or in hot springs on volcanic islands, or perhaps even deep in the Earth's crust where they could tap chemical energy from rock-water interactions. For perhaps 1 billion years, life remained microscopic and relatively simple, slowly spreading through Earth's oceans and possibly onto land in the form of microbial mats. But these simple organisms were transforming the planet in profound ways. They were creating new minerals through their metabolic processes, laying down the first sedimentary rocks that incorporated biological materials. They were beginning to alter the chemistry of the oceans and atmosphere, though the changes were slow and subtle at first. Then around 3.5 billion years ago, one of the most important innovations in the history of life emerged: photosynthesis. The first photosynthetic organisms didn't produce oxygen. They used different chemical pathways, perhaps splitting hydrogen sulfide instead of water. But they had learned to capture energy from sunlight, no longer dependent solely on chemical energy from the Earth. This was a revolutionary development, opening up a vast new energy source that would eventually power most of life on Earth. The earliest evidence for photosynthesis comes from structures called stromatolites, layered rocks formed by mats of photosynthetic bacteria. These bacteria would grow toward the light during the day, then be covered by sediment, only to grow through it again the next day, creating distinctive layered patterns that we can still see in ancient rocks billions of years later. These stromatolites dominated shallow marine environments for billions of years, growing in vast reefs that lined the shores of the ancient continents. Their photosynthetic creators slowly but steadily pumping out a waste product that would eventually transform the world: oxygen. At first, the oxygen produced by these early photosynthesizers didn't accumulate in the atmosphere. The early Earth was full of oxygen-hungry elements like iron and sulfur that would immediately react with any free oxygen, locking it away in minerals. The oceans were full of dissolved iron, and as oxygen was produced, it combined with this iron to form iron oxides that settled to the ocean floor. These formed distinctive red and black striped rocks called banded iron formations, which we find in ancient rocks around the world, a geological record of this titanic chemical battle between oxygen production and oxygen consumption. For perhaps 1 billion years, this process continued, with photosynthetic bacteria producing oxygen that was immediately consumed by chemical reactions. But slowly, gradually, the oxygen-hungry elements were being used up. The oceans were being swept clean of dissolved iron, the exposed rocks on land were being oxidized, and the reduced gases in the atmosphere were being converted to oxidized forms. And then, around 2.5 billion years ago, something momentous happened. The oxygen sinks were finally overwhelmed, and free oxygen began to accumulate in the atmosphere for the first time. This was the Great Oxidation Event, one of the most significant changes in Earth's history. From our oxygen-breathing perspective, this might seem like a wonderful development, but for most life on Earth at the time, it was a catastrophe. Oxygen is a highly reactive gas, toxic to organisms that evolved in its absence. The Great Oxidation Event caused the first mass extinction in Earth's history, wiping out countless species of anaerobic bacteria that couldn't tolerate the new atmospheric conditions. They retreated to oxygen-free environments like deep mud, the guts of other organisms, and hot springs, where their descendants live to this day. Meanwhile, organisms that could tolerate or even use oxygen thrived, taking over the newly oxygenated environments. The rise of oxygen had other profound effects on Earth's climate. Methane, a powerful greenhouse gas that had been abundant in the early atmosphere, was oxidized to carbon dioxide and water. Since methane is a much more effective greenhouse gas than carbon dioxide, this transformation caused a dramatic cooling of the planet. Earth plunged into its first global glaciation, the Huronian glaciation, with ice sheets extending all the way to the equator. For 300 million years, Earth was locked in this deep freeze, a snowball Earth that reflected most of the sun's energy back to space. Life survived this frozen catastrophe in refugia, perhaps near volcanic hot springs, or in areas where the ice was thin enough for sunlight to penetrate. Eventually, volcanic carbon dioxide built up in the atmosphere to levels high enough to trigger a super greenhouse effect, melting the ice in a geological instant. The planet swung from frozen to tropical in perhaps just a few thousand years, with torrential rains weathering the exposed rocks and washing nutrients into the oceans, triggering blooms of photosynthetic life that would once again transform the atmosphere. During this time of atmospheric upheaval, another revolutionary development was taking place in the oceans. Somewhere, somehow, a larger cell engulfed a smaller bacterium, but instead of digesting it, the two formed a partnership. The bacterium continued to live inside the larger cell, providing it with energy through respiration, while the host cell provided protection and nutrients. This symbiotic relationship became permanent, with the engulfed bacteria evolving into mitochondria, the powerhouses of the cell. This was the birth of the eukaryotes, organisms with complex cells containing internal compartments and specialized structures. The evolution of eukaryotic cells opened up entirely new possibilities for life. These cells were much larger than bacteria, with volumes thousands of times greater, allowing for increased complexity and specialization. They had a nucleus to protect their genetic material, an internal skeleton to maintain their shape, and the ability to engulf and digest other cells. Some eukaryotes later engulfed photosynthetic cyanobacteria, which became chloroplasts, creating the first algae and eventually plants. These serial endosymbiosis events, where one organism permanently incorporated another, were pivotal moments that set the stage for all complex life on Earth. For another billion years, life remained single-celled, though eukaryotic cells were becoming increasingly sophisticated. They developed sexual reproduction, mixing genetic material from two parents to create offspring with new combinations of genes, greatly accelerating evolution. They evolved complex internal structures like the endoplasmic reticulum for protein synthesis and the Golgi apparatus for packaging and shipping cellular products. Some developed the ability to change shape, extending pseudopods to move and capture prey. Others evolved rigid cell walls and lived as floating photosynthetic plankton. Then around 1.5 billion years ago, another breakthrough occurred. Some eukaryotic cells began living together in colonies, cooperating for mutual benefit. At first, these were simple aggregations where all cells were essentially identical, like modern slime molds that can exist as individual cells or come together into a multicellular slug when conditions require it. But over time, cells within these colonies began to specialize, taking on different roles. Some cells handled reproduction, others formed protective outer layers. Still others specialized in gathering food or providing structural support. This transition to multicellularity happened independently multiple times in different lineages, leading to the diverse array of multicellular life we see today. Red algae, green algae, brown algae, fungi, and animals all evolved multicellularity separately, each finding their own solutions to the challenges of coordinating multiple cells. The key innovation was the evolution of cell-to-cell communication systems, allowing cells to coordinate their activities and work together as a single organism rather than just a colony of individuals. By 800 million years ago, the first true animals had evolved, though they were nothing like the animals we know today. These were soft-bodied creatures, probably similar to modern sponges or jellyfish, living on the seafloor or floating in the water column. They fed by filtering small particles from the water or capturing other microscopic organisms. They had no eyes, no brains, no complex organs, just simple tissues organized into basic body plans. But they were truly multicellular, with specialized cell types and coordinated development from a single fertilized egg. The Earth during this time was experiencing another series of severe ice ages, the cryogenian glaciations, which may have covered the entire planet in ice once again. These snowball Earth events, lasting from about 750 to 580 million years ago, were even more severe than the earlier Huronian glaciation. Ice sheets miles thick covered the oceans, with only the deepest waters remaining liquid. Life survived in pockets of open water maintained by volcanic heat, or in thin films of liquid water within the ice itself, where enough sunlight could penetrate for photosynthesis. When the ice finally melted, around 580 million years ago, it revealed a transformed world. The breakup of the supercontinent Rodinia had created new shallow seas perfect for marine life. Oxygen levels had risen to near modern levels, providing abundant energy for active animals. And in these newly hospitable seas, life exploded in diversity. This was the Ediacaran period, named after the Ediacara Hills in Australia, where fossils from this time were first discovered, and it saw the evolution of the first large complex animals. The Ediacaran fauna were bizarre by modern standards, unlike anything alive today. There were frond-like creatures that looked more like plants than animals, anchored to the seafloor and swaying in the currents. There were quilted, mattress-like organisms that may have harboured photosynthetic bacteria in their tissues. There were disc-shaped creatures with threefold symmetry, completely unlike the bilateral symmetry that dominates the animal kingdom today. And there were the first mobile animals, leaving tracks and burrows in the seafloor as they searched for food. These Ediacaran organisms represented evolution's first experiments with large body size and complex morphology. Some, like Dickinsonia, could grow over a metre long, though they were only a few millimetres thick, maximising their surface area for oxygen absorption in the still relatively low oxygen seas. Others, like Kimberella, showed the first evidence of a front and back end, with possible scratching marks suggesting they grazed on microbial mats. The period also saw the evolution of the first predators, though predation was probably limited to microscopic prey or scavenging on dead organisms. Then, 541 million years ago, something extraordinary happened. In a geological instant, the fossil record exploded with new forms of life. This was the Cambrian explosion, the most dramatic diversification event in the history of life on Earth. Within just 20 million years, virtually every major group of animals that exist today appeared in the fossil record. Arthropods with jointed legs and external skeletons, mollusks with shells, echinoderms with fivefold symmetry, chordates with notochords that would eventually become backbones, all appeared seemingly simultaneously in rocks around the world. The Cambrian seas were filled with creatures that seem almost alien to modern eyes. There was Anomalocaris, a 2-metre-long predator with grasping arms and compound eyes, the terror of the Cambrian seas. There was Opobinia, with 5 eyes and a long, flexible proboscis ending in a grasping claw. There was Hallucigenia, initially reconstructed upside down, because paleontologists couldn't figure out which were legs and which were defensive spines. And there were trilobites, those iconic arthropods with their distinctive 3-lobed bodies and compound eyes made of crystalline calcite, which would dominate the seas for the next 270 million years. The Cambrian explosion also saw the evolution of complex ecosystems with multiple trophic levels. There were filter feeders straining plankton from the water, deposit feeders processing seafloor sediments, grazers scraping algae from rocks, active predators hunting mobile prey, and scavengers cleaning up the remains. Arms races between predators and prey drove the evolution of defensive structures like shells and spines, and offensive structures like claws and teeth. Eyes evolved independently in multiple lineages, from simple light-detecting spots to sophisticated compound eyes capable of forming images. One particularly important group that appeared during the Cambrian were the early chordates, our own distant ancestors. Creatures like Picaia and Hyquithis had notochords, flexible rods running along their backs that provided structural support, and V-shaped muscle blocks that allowed for efficient swimming. They had primitive heads with sense organs concentrated at the front end, and some even had primitive skulls protecting their nascent brains. These small, insignificant-looking swimmers, no more than a few centimetres long, carried within them the blueprint for all future vertebrates. Following the Cambrian explosion, life continued to diversify through the Ordovician period, from 485 to 443 million years ago. The seas were dominated by marine invertebrates, with coral reefs appearing for the first time, built by tabulate and rugose corals very different from modern reef builders. Cephalopods, the group that includes modern octopi and squid, evolved shells, and became top predators, with some reaching lengths of 6 meters or more. The first fish with jaws evolved, revolutionizing vertebrate feeding and setting the stage for their eventual dominance. But the Ordovician ended with catastrophe. The Ordovician-Silurian extinction event, triggered by a severe ice age, possibly caused by the weathering of newly formed mountains or a gamma-ray burst from a nearby supernova, wiped out 85% of marine species. Entire groups disappeared forever, while others were reduced to a handful of survivors. Yet life rebounded, as it always does, with the survivors radiating into the empty ecological niches left by the extinction. During the Silurian period, from 443 to 419 million years ago, one of the most momentous transitions in the history of life began: the colonization of land. The continents, which had been barren rock and sand since their formation, began to turn green. The first land plants evolved from green algae, developing waxy cuticles to prevent water loss, stomata to regulate gas exchange, and eventually vascular tissues to transport water and nutrients. These early plants were small and simple, similar to modern mosses and liverworts, growing in damp areas near water. The colonization of land by plants fundamentally changed Earth's surface. Plant roots broke down rocks, accelerating weathering and soil formation. They altered the water cycle, with transpiration returning water to the atmosphere. They changed the planet's albedo, with green plants absorbing more sunlight than bare rock. And they pulled carbon dioxide from the atmosphere through photosynthesis, gradually cooling the planet and increasing oxygen levels even further. Plants weren't alone in colonizing the land. Fungi had probably been on land even earlier, and they formed crucial partnerships with plants, mycorrhizal associations where fungi helped plants absorb nutrients and water in exchange for sugars from photosynthesis. Arthropods followed, with early arachnids and myriapods feeding on plant matter and each other. These early terrestrial ecosystems were simple, concentrated along waterways and in constantly moist environments. But they were the beginning of the terrestrial biosphere that would eventually rival the oceans in diversity and biomass. The Devonian period, from 419 to 358 million years ago, is often called the Age of Fishes, and for good reason. The seas were dominated by an incredible diversity of fish, from the heavily armoured placoderms with their bone-crushing jaws to the first sharks with their cartilaginous skeletons and replaceable teeth. Ray-finned fish, the group that includes most modern fish, appeared and began their rise to dominance. And most significantly for us, lobe-finned fish evolved, with their muscular fins supported by bones that would eventually become the limbs of tetrapods. On land, the Devonian saw the first forests. Plants evolved true roots, allowing them to grow taller and access deeper water sources. They developed wood, providing structural support for increasing height. By the late Devonian, trees like Archaeopteris reached heights of 30 meters or more, forming the first forest canopies. These forests were still concentrated along waterways, but they were spreading inland, transforming vast areas of previously barren land into complex ecosystems. The transition from water to land by vertebrates happened in these Devonian wetlands. Fish like Tiktaalik evolved muscular fins that could support their weight, allowing them to prop themselves up in shallow water, or even venture briefly onto land. They developed lungs alongside their gills, able to breathe air when water became oxygen poor. Their skulls flattened and their eyes moved to the top of their heads, adaptations for peering above the water surface. By the end of the Devonian, the first true tetrapods had evolved, four-limbed vertebrates that could walk on land, though they still returned to water to reproduce. The Devonian ended with another mass extinction, possibly caused by the evolution of land plants itself. As plants spread across the continents, their roots broke down rocks and released nutrients that washed into the oceans, causing massive algal blooms. When these algae died and decomposed, they consumed oxygen, creating vast dead zones in the oceans. Combined with climate change from the drawdown of atmospheric carbon dioxide by plants, this led to the late Devonian extinction, which particularly devastated marine life, wiping out the placoderms and many other groups. The Carboniferous period, from 358 to 298 million years ago, saw the Earth transformed into a hothouse world of swamp forests and giant insects. Atmospheric oxygen levels reached 35%, compared to 21% today, allowing arthropods to grow to enormous sizes. Dragonflies with 70-centimetre wingspans patrolled the skies. Millipedes 2 metres long crawled through the leaf litter. Scorpions the size of dogs hunted in the undergrowth. The high oxygen also made the atmosphere highly flammable, with wildfires common in the coal forests. These coal forests were dominated by tree-sized club mosses, horsetails and ferns, very different from modern forests. Lepidodendron trees grew 40 metres tall with trunks 2 metres in diameter, yet they were essentially giant club mosses, reproducing by spores rather than seeds. The climate was warm and humid, with no polar ice caps, and vast swamps covered much of the tropical land masses. When these plants died, they fell into the oxygen-poor swamp water, where they couldn't fully decompose, gradually accumulating as thick layers of peat that would eventually become the coal deposits that powered the Industrial Revolution. Vertebrates were diversifying rapidly on land during the Carboniferous. Amphibians dominated the wetlands, some growing to crocodile size as apex predators. But a new group was evolving that would eventually displace them: the amniotes, vertebrates that could lay eggs on dry land. The amniotic egg, with its protective membranes and shell, freed vertebrates from their dependence on water for reproduction. This key innovation allowed them to colonize dry environments far from water, opening up vast new territories for vertebrate life. The amniotes quickly split into two major lineages. The synapsids, characterized by a single temporal fenestra opening in the skull behind each eye socket, would eventually give rise to mammals. The sauropsids, with two temporal fenestrae, would give rise to reptiles, including dinosaurs and birds. During the late Carboniferous and early Permian, it was the synapsids that dominated, with sail-backed predators like Dimetrodon, often mistakenly called a dinosaur, ruling the land. The Permian period, from 298 to 252 million years ago, saw the assembly of the supercontinent Pangaea, with almost all of Earth's land masses joined into a single, vast continent stretching from pole to pole. The interior of this supercontinent was extremely arid, with vast deserts far from any ocean. The climate became increasingly seasonal, with monsoons along the coasts and extreme temperature variations in the continental interior. These harsh conditions drove the evolution of many adaptations for dealing with aridity, including more efficient kidneys, better water retention, and behavioural adaptations like burrowing. The dominant land vertebrates of the Permian were the therapsids, advanced synapsids, that were developing increasingly mammal-like characteristics. They evolved differentiated teeth for cutting and grinding food, rather than the simple cone-shaped teeth of earlier vertebrates. They developed more upright postures with legs positioned beneath their bodies rather than sprawling to the sides. Some even evolved whiskers and possibly fur, adaptations for sensing their environment and regulating body temperature. Groups like the cynodonts were well on their way to becoming true mammals. But the Permian ended with the most catastrophic event in the history of life, the Permian Triassic extinction event, also known as the Great Dying. 252 million years ago, Massive volcanic eruptions in what is now Siberia released enormous amounts of carbon dioxide and other gases into the atmosphere. The eruptions continued for hundreds of thousands of years, pouring out enough lava to cover an area the size of Europe. The carbon dioxide caused extreme global warming, while sulfur compounds caused acid rain. The warming oceans became stratified and oxygen depleted, creating vast dead zones. The extinction was devastating beyond imagination. 96% of marine species went extinct. 70% of terrestrial vertebrate species disappeared. Insects suffered their only mass extinction. Entire ecosystems collapsed. The forests died back, replaced by opportunistic ferns and fungi. The coral reefs disappeared entirely and wouldn't recover for 10 million years. It was the closest life on Earth has ever come to complete annihilation, with some estimates suggesting that only 5% of species survived. The early Triassic world that emerged from this catastrophe was a desolate place. The few survivors faced a hot, arid world with unstable ecosystems. Disaster taxa opportunistic species that could thrive in disturbed environments dominated for millions of years. The mammal-like therapsids that had ruled the Permian were reduced to a few small survivors. But in this emptied world, a new group began to diversify. The archosaurs, the group that would give rise to crocodiles, pterosaurs, and dinosaurs. The first dinosaurs appeared in the Middle Triassic, around 230 million years ago. They were small, bipedal animals, no larger than a chicken, with long tails and grasping hands. They had upright postures with legs directly beneath their bodies, allowing for more efficient locomotion than the sprawling gait of other reptiles. They had air sacs connected to their lungs, providing more efficient respiration, an adaptation that would later allow some of their descendants to grow to enormous sizes. At first, dinosaurs were minor components of their ecosystems, overshadowed by other archosaurs and the remaining therapsids. The Triassic ended with another mass extinction 201 million years ago, possibly caused by volcanic eruptions associated with the breakup of Pangaea. This extinction eliminated many of the dinosaurs' competitors, clearing the way for their rise to dominance. The Jurassic period, from 201 to 145 million years ago, was the beginning of the age of dinosaurs. They diversified rapidly into numerous ecological niches, from tiny feathered insectivores to long-necked sauropods that were the largest animals ever to walk the earth. The Jurassic saw the evolution of many iconic dinosaur groups. Sauropods like Brachiosaurus and Diplodocus evolved extremely long necks that allowed them to browse vegetation other herbivores couldn't reach, growing to lengths of 30 meters or more and weights exceeding 50 tons. Theropods like Allosaurus became apex predators with powerful jaws and serrated teeth. Stegosaurs evolved rows of plates and spikes for display and defense, and small feathered theropods began experimenting with gliding and powered flight, leading to the evolution of birds by the late Jurassic. The first bird, Archaeopteryx, appeared about 150 million years ago, a transitional form with features of both dinosaurs and modern birds. It had feathers and wings capable of flight, but also teeth, clawed fingers, and a long bony tail. Birds were essentially small, flying dinosaurs, and they would be the only dinosaur lineage to survive the coming catastrophe. During the Jurassic, they were just one of many experiments in flight, competing with pterosaurs, the flying reptiles that dominated the skies, with some species achieving wingspans of 10 meters or more. The Jurassic also saw major developments in other groups. Mammals, reduced to small nocturnal creatures since the Permian extinction, were quietly diversifying in the shadows of the dinosaurs. They evolved true mammalian characteristics like hair, milk production, and specialized teeth. Different lineages experimented with various lifestyles. Some were burrowers, others climbed trees, some even evolved gliding membranes. Marine reptiles like ichthyosaurs, plesiosaurs, and marine crocodiles ruled the seas, occupying the ecological niches of modern whales and dolphins. The Cretaceous period, from 145 to 66 million years ago, was the height of the age of dinosaurs. The supercontinent Pangaea had broken apart, with the Atlantic Ocean widening as the Americas separated from Europe and Africa. This geographic isolation led to increased diversity as dinosaur populations evolved separately on different continents. The climate was warm and humid with no polar ice caps, and sea levels were much higher than today, with shallow seas covering much of the continental interiors. The Cretaceous saw the evolution of flowering plants, or angiosperms, one of the most important developments in the history of life. Flowers allowed for more efficient reproduction through partnerships with animal pollinators, while fruits encouraged animals to disperse seeds. Flowering plants diversified rapidly, developing relationships with insects, birds, and mammals that would shape terrestrial ecosystems to this day. By the end of the Cretaceous, they had largely displaced the conifers, ferns, and cycads that had dominated earlier periods. Dinosaurs reached their peak diversity in the Cretaceous. Tyrannosaurus rex, perhaps the most famous dinosaur, evolved in the late Cretaceous, reaching lengths of 12 meters and weights of 9 tons, with the most powerful bite of any terrestrial animal. Triceratops and other ceratopsians evolved elaborate horns and frills for defense and display. Hadrosaurs developed complex teeth batteries for processing tough plant material. Ankylosaurs became living tanks with armor plating and club tails. And various small theropods continued evolving increasingly bird-like features, with some developing powered flight independent of the bird lineage. But this golden age of dinosaurs was about to end abruptly. 66 million years ago, a 10-kilometer-wide asteroid slammed into the Yucatan Peninsula at a speed of 20 kilometers per second. The impact released energy equivalent to billions of nuclear bombs, creating a crater 180 kilometers wide. The immediate effects were catastrophic. A fireball that incinerated everything within 1,000 kilometers, earthquakes of magnitude 11 or higher, and tsunamis hundreds of meters tall that devastated coastlines around the world. But the worst was yet to come. The impact threw billions of tons of rock and dust into the atmosphere, along with sulfur compounds from the evaporated bedrock. This created a cloud that blocked sunlight for months, possibly years, causing a nuclear winter effect. Photosynthesis shut down globally, causing the collapse of food chains. Acid rain from the sulfur compounds poisoned lakes and streams. When the dust finally settled and sunlight returned, carbon dioxide from the impact and subsequent wildfires caused extreme greenhouse warming. It was a 1-2 punch that few organisms could survive. The Cretaceous Paleogene extinction event wiped out all non-avian dinosaurs, along with pterosaurs, marine reptiles, ammonites, and many other groups. In total, about 75% of species went extinct. But some organisms survived. Birds, the only remaining dinosaurs, small mammals that could shelter in burrows and required less food, crocodilians in freshwater environments that were partially buffered from the worst effects, and various plants and insects that could survive as seeds or eggs through the catastrophe. In the aftermath of the extinction, the world was once again emptied of its dominant life forms, and the survivors radiated into the vacant ecological niches. This was the beginning of the Cenozoic era, the age of mammals. Within just a few million years, mammals diversified from mostly small shrew-like creatures into a vast array of forms. Some returned to the oceans, evolving into whales and dolphins. Others took to the trees, becoming primates. Some grew to enormous sizes, like the Indricotherium, a hornless rhinoceros relative that stood 5 meters tall at the shoulder. The early Cenozoic, particularly the Paleocene and Eocene epochs, from 66 to 34 million years ago, was a warm world with no permanent ice at the poles. Tropical forests extended into the Arctic, with palm trees and crocodilians living in areas that are now frozen tundra. This greenhouse world reached its peak during the Paleocene-Eocene thermal maximum 56 million years ago, when global temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years, possibly due to the release of methane from seafloor deposits. During this warm period, many modern mammal groups appeared and diversified. The first true primates evolved, small tree-dwelling creatures with grasping hands and forward-facing eyes for better depth perception. Horses appeared as small dog-sized forest dwellers with multiple toes. Whales evolved from land-dwelling ancestors, with transitional forms, like Ambulocetus, showing adaptations for both terrestrial and aquatic life. Bats took to the air, the only mammals to evolve powered flight, and grasses began their spread across the continents, though they wouldn't dominate until much later. The climate began cooling around 50 million years ago, driven by various factors including the separation of Antarctica from South America and Australia, which allowed the Antarctic circumpolar current to form, isolating Antarctica and allowing ice sheets to develop. The collision of India with Asia, beginning around 50 million years ago, pushed up the Himalayas, and the weathering of these new mountains pulled carbon dioxide from the atmosphere. By 34 million years ago, at the Eocene-Oligocene boundary, Antarctica had developed permanent ice sheets, marking the beginning of the current ice age, though it wouldn't reach full intensity for millions of years. As the climate cooled and dried through the Oligocene and Miocene epochs, from 34 to 5 million years ago, forests retreated and grasslands expanded. This drove the evolution of many modern ecosystem types, from savannas to prairies to steppes. Grazing mammals evolved high-crowned teeth to deal with the silica in grasses that wore down teeth rapidly. They developed longer legs for running in open environments and complex stomachs for digesting tough plant material. Predators evolved to hunt in these open environments, developing pursuit hunting strategies rather than ambush tactics. In Africa, the primates were undergoing their own evolutionary journey. By 25 million years ago, the first apes had appeared, larger than monkeys and lacking tails, with more flexible shoulders for swinging through trees. These early apes diversified throughout Africa and Eurasia during the Miocene, with dozens of species occupying various forest habitats. But as forests contracted and grasslands expanded, some apes began spending more time on the ground, developing adaptations for terrestrial life. Around 7 million years ago, in Africa, one lineage of apes began a fateful evolutionary journey. These early hominins, as we call the human lineage after our split from chimpanzees, developed the ability to walk upright on 2 legs, though they still spent considerable time in trees. Bipedalism freed their hands for carrying food and tools, and may have been more energy efficient for travelling between scattered food sources in increasingly open environments. Species like Sahelanthropus, Orrorin, and Ardipithecus represent these early experiments in bipedalism. By 4 million years ago, the Australopithecines had evolved, fully bipedal apes with brains only slightly larger than chimpanzees. Australopithecus afarensis, including the famous Lucy fossil, walked upright across the African savanna 3.2 million years ago, though they retained long arms and curved fingers for climbing. They used simple tools, probably wooden implements that haven't preserved, and may have begun the cultural transmission of knowledge that would become humanity's hallmark. Around 2.8 million years ago, the genus Homo appeared, marked by larger brains, and the first manufactured stone tools. Homo habilis, the handyman, created the Oldowan tool industry, simple choppers and flakes used for processing meat and plants. This dietary shift toward more meat eating, enabled by tools, may have provided the calories necessary for evolving larger energy-hungry brains. It also required greater cooperation, and possibly the beginnings of language for coordinating hunting and gathering activities. Homo erectus appeared around 2 million years ago with a brain nearly twice the size of Australopithecines and a fully modern body plan, with long legs and shorter arms. They were the first hominins to leave Africa, spreading across Asia and Europe by 1.8 million years ago. They mastered fire by at least 400,000 years ago, and possibly much earlier, providing warmth, protection, and the ability to cook food, which made more calories available and may have driven further brain evolution. They created sophisticated stone tools, including hand axes that required planning and skill to manufacture. The climate during this period was becoming increasingly unstable, with ice ages cycling every 41,000 years, then shifting to 100,000-year cycles around 1 million years ago. These climate oscillations, driven by variations in Earth's orbit and axis tilt, created constantly changing environments that may have selected for intelligence and adaptability. During glacial periods, ice sheets covered much of northern Europe and North America, lowering sea levels and creating land bridges between continents. During interglacials, the climate was often warmer than today, with forests extending into the Arctic. By 500,000 years ago, hominin brains had expanded to nearly modern size, and multiple species of humans coexisted across Africa and Eurasia. Homo heidelbergensis in Africa and Europe, Homo erectus in Asia, and later Homo neanderthalensis in Europe and Western Asia, and the mysterious Denisovans in Asia, all developed sophisticated cultures with complex tool-making, controlled use of fire, and possibly symbolic behaviour. Neanderthals buried their dead with grave goods, created art, and had brains as large or larger than modern humans. Our own species, Homo sapiens, appeared in Africa around 300,000 years ago, distinguished by a more globular skull, smaller faces and teeth, and perhaps most importantly, a cognitive revolution that gave us fully modern language and symbolic thinking. By 100,000 years ago, we were creating jewellery, painting cave walls, and engaging in long-distance trade. We developed new technologies like projectile weapons, sewn clothing, and watercraft that allowed us to colonize new environments. Beginning around 70,000 years ago, modern humans began spreading out of Africa in earnest, though earlier migrations had occurred. We spread along the coasts of Asia, reaching Australia by 65,000 years ago, requiring sea crossings that demonstrated planning and sophisticated technology. We moved into Europe by 45,000 years ago, encountering and interbreeding with Neanderthals. We crossed the Bering Land Bridge into the Americas by at least 15,000 years ago, possibly much earlier, rapidly spreading to the southern tip of South America. Wherever humans went, the megafauna disappeared. Mammoths, giant ground sloths, saber-toothed cats, giant wombats, and hundreds of other large species went extinct shortly after humans arrived on each continent. Whether through hunting, habitat modification, or introduced diseases, humans fundamentally altered every ecosystem we entered. By 10,000 years ago, we were the only human species left, having outlasted or absorbed all our close relatives, and we'd spread to every continent except Antarctica. The invention of agriculture around 12,000 years ago in multiple locations independently, the Fertile Crescent, China, Mesoamerica, the Andes, Sub-Saharan Africa, and New Guinea transformed human society and the planet itself. We began modifying entire landscapes, clearing forests for fields, irrigating deserts, and selectively breeding plants and animals until they bore little resemblance to their wild ancestors. Wheat, corn, rice, and other crops became dependent on humans for survival, while we became dependent on them for food. Agriculture allowed for food surpluses and permanent settlements, leading to population explosions and the development of complex societies. Villages grew into cities, cities into states, states into empires. Writing developed independently in Mesopotamia, Egypt, China, and Mesoamerica to keep track of agricultural surpluses and commercial transactions. Technologies like metallurgy, the wheel, and sailing ships spread along trade networks that eventually connected most of the world. Religions, philosophies, and scientific traditions emerged to make sense of our place in the universe, each culture developing its own understanding of time, existence, and meaning. The pace of change, which had been measured in millions of years for most of Earth's history, then thousands of years during human evolution, now accelerated to centuries and decades. The Bronze Age gave way to the Iron Age. Classical civilizations rose and fell, and ideas spread along silk roads and sea routes. The scientific revolution, just 400 years ago, fundamentally changed how we understand the world, replacing mythological explanations with natural laws and mathematical descriptions. The Industrial Revolution, 200 years ago, harnessed fossil fuels, those compressed remains of carboniferous forests, unleashing energy that transformed human society and began altering the planet's climate. In just the last century, we've split the atom, decoded DNA, walked on the moon, and connected the world through the internet. We've discovered that the universe is expanding, that we're made of stardust, that we share common ancestors with all life on Earth. We've begun to understand our place in cosmic history, from the Big Bang to the present moment. And now, as you lie here listening to this story, you are the latest moment in this vast continuum. 13.8 billion years of cosmic evolution focused into your conscious experience of this present instant. But the story doesn't end here. Time continues its relentless march forward, and the future stretches out before us, vast and uncertain, but governed by the same physical laws that have shaped everything that came before. Let's drift forward now, beyond the present moment, into the deep future that awaits our planet, our species, and our universe. In the near future, measured in decades and centuries, human civilization will face critical challenges and opportunities. Climate change from our carbon emissions is already altering weather patterns, melting ice caps, and raising sea levels. The Earth's temperature will continue rising for decades, even if emissions stop today, as the climate system has tremendous inertia. Coastal cities will flood, deserts will expand, and ecosystems will shift toward the poles. Species are going extinct at rates not seen since the asteroid impact that killed the dinosaurs, a sixth mass extinction driven by human activity. Yet humans are remarkably adaptable, and technology continues advancing at an exponential rate. Renewable energy sources are becoming cheaper than fossil fuels, potentially ending our dependence on ancient sunlight stored in coal and oil. Genetic engineering and synthetic biology offer the possibility of designing organisms to clean up pollution, produce food more efficiently, or even revive extinct species. Artificial intelligence is beginning to match and exceed human capabilities in specific domains, potentially leading to a transformation as profound as the agricultural or industrial revolutions. Looking ahead thousands of years, assuming human civilization survives its current challenges, we might spread throughout the solar system. Mars could be terraformed, its thin atmosphere thickened and warmed until liquid water flows on its surface again, for the first time in billions of years. Rotating space habitats could house millions of people, creating new branches of humanity adapted to different gravitational conditions. The moons of Jupiter and Saturn, with their subsurface oceans, might harbour not just human colonies but perhaps indigenous life that evolved independently from Earth. On Earth itself, the continents will continue their slow dance across the planet's surface. Africa is splitting apart along the East African Rift, and in 10 million years, a new ocean will separate Eastern Africa from the rest of the continent. Australia is moving northward at about 7 centimetres per year, and in 50 million years, it will collide with Asia, pushing up new mountain ranges. The Atlantic Ocean continues widening while the Pacific shrinks, and in 200 million years, the Americas might collide with Asia, forming a new supercontinent that some scientists call Pangaea Ultima. The climate will continue cycling between ice ages and warm periods, driven by variations in Earth's orbit, at least until human activities or natural processes overwhelm these cycles. In 50,000 years, we'll enter the next glacial period naturally, unless greenhouse gases prevent it. Niagara Falls will erode back to Lake Erie and disappear. The Hawaiian Islands will erode below sea level, while new volcanic islands emerge from the Hawaiian hotspot. Mountain ranges will rise and fall, ground down by erosion and pushed up by tectonic forces, recycling Earth's surface as they have for billions of years. Life will continue evolving, shaped by whatever environments exist. If humans disappear, other species will adapt to the cities and structures we leave behind, just as life today thrives in environments created by previous generations of organisms. Rats might grow larger in our absence, filling ecological niches left vacant. Plants will break through concrete and asphalt, gradually erasing our roads and buildings. Nuclear waste sites will create pockets of radiation that might accelerate evolution, producing new forms adapted to high radiation environments. The plastic we've produced will gradually break down, but some bacteria are already evolving to digest it, turning our pollution into food. In 1 million years, almost all traces of human civilization will have vanished. Our cities will be geological layers compressed into rock strata that future paleontologists, human or otherwise, might study to understand this brief moment when one species transformed a planet. Only a few traces will remain: altered isotope ratios in sediments, a layer of plastic particles in rock formations, perhaps some fossilized bones and teeth. The faces on Mount Rushmore might still be vaguely recognizable, eroded but preserved by the granite's durability. Radio signals from our broadcasts will still be expanding through space, carrying our voices and images to distant stars, though increasingly faint and scattered. 10 million years from now, Earth might look completely alien to modern eyes. Evolution will have produced new forms we can't imagine, just as the dinosaurs couldn't have imagined mammals, or the first fish couldn't have conceived of flight. Perhaps descendants of birds will develop higher intelligence, their efficient respiratory systems, and lightweight bones allowing them to evolve large brains while maintaining flight. Maybe cephalopods will colonize the land, their flexible bodies and problem-solving abilities giving rise to a terrestrial civilization. Or perhaps something entirely unexpected will emerge, evolution taking paths we cannot predict. The sun is slowly growing brighter as it ages, increasing in luminosity by about 1% every 100 million years. In 500 million years, this brightening will begin to have serious consequences for life on Earth. The increased solar radiation will accelerate the weathering of silicate rocks, which removes carbon dioxide from the atmosphere. As CO2 levels drop, plants will struggle to photosynthesize. C3 photosynthesis, used by most plants including trees, will become impossible first. C4 plants like grasses might survive longer, but eventually even they will fail. The death of plants will cause atmospheric oxygen to plummet as it's no longer replenished, making animal life impossible. In about 600 million years, only microbes will remain, clustered around volcanic vents or deep underground where conditions remain stable. The Earth will have returned to something resembling its earliest state, a planet of single-celled organisms eking out existence in extreme environments. The complex dance of predator and prey, the beauty of flowers and birdsong, the intricacy of ecosystems that took billions of years to develop, will all be memories encoded in rock strata. 1 billion years from now, the sun's increasing brightness will trigger a runaway greenhouse effect. The oceans will begin evaporating, water vapor will fill the atmosphere, and surface temperatures will soar. Water vapor is a powerful greenhouse gas, so more evaporation leads to more warming, which causes more evaporation in a feedback loop that ends only when all the water has either escaped to space or been broken down by ultraviolet radiation. Earth will become like Venus, with surface temperatures hot enough to melt lead and a thick, suffocating atmosphere. But the sun's story is far from over. In 5 billion years, it will begin running out of hydrogen fuel in its core. The core will contract and heat up while the outer layers expand enormously. The sun will become a red giant, swelling to perhaps 200 times its current diameter. Mercury and Venus will be engulfed and vaporized. Earth's fate is uncertain. The sun will lose mass as it expands, causing Earth's orbit to spiral outward, but it might not move fast enough to escape being swallowed. Even if Earth survives, it will be a charred cinder, its atmosphere stripped away, its surface melted and re-solidified. The sun will spend about 1 billion years as a red giant, fusing helium in its core and hydrogen in a shell around the core. It will pulsate, varying in brightness and size, and stellar winds will blow away its outer layers into space, creating a beautiful planetary nebula that will glow for thousands of years. Eventually, all that will remain is the sun's core, a white dwarf about the size of Earth but containing half the sun's original mass. This white dwarf will be incredibly dense, a teaspoon of its material weighing as much as a car. The white dwarf that was once our sun will cool slowly over trillions of years, its initial temperature of hundreds of thousands of degrees gradually dropping toward absolute zero. It will crystallize, its carbon and oxygen atoms arranging themselves into a giant crystal structure, essentially a diamond the size of Earth. After perhaps a quadrillion years, it will have cooled to the point where it emits no visible light, becoming a black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. Meanwhile, the universe itself continues evolving on even grander scales. Galaxies are still colliding and merging, building ever larger structures. Our Milky Way will collide with the Andromeda Galaxy in about 4 billion years, the two spirals dancing around each other and eventually merging into a giant elliptical galaxy. The collision will trigger new bursts of star formation as gas clouds compress, but individual stars are so far apart that few, if any, will actually collide. Our solar system, if it still exists, will likely be flung into a different orbit, but otherwise survive intact. Over the next hundreds of billions of years, star formation will gradually slow and cease. The universe is expanding and cooling, and the gas needed to form new stars is being locked away in existing stars, stellar remnants, and black holes. Smaller, redder stars will dominate as they burn their fuel much more slowly than stars like our Sun. The longest-lived stars, red dwarfs with less than 10% of the Sun's mass, can shine for trillions of years, slowly converting hydrogen to helium in their cores. The last stars to form will be strange objects unlike anything in today's universe. As heavy elements from generations of supernovae accumulate, future stars will be incredibly enriched in metals, allowing them to be much smaller and cooler than current stars. These final stars might be frozen stars, brown dwarfs just massive enough to sustain fusion, glowing dimly for hundreds of trillions of years. When the last of these stars dies, the stelliferous era, the age of stars, will end. In about 100 trillion years, the universe will enter what cosmologists call the degenerate era. All the stars will have died, leaving only their remnants, white dwarfs, neutron stars, and black holes. Planets will still orbit these dead stars for a while, but gravitational interactions with passing objects will eventually strip them away. Over unimaginable timescales measured in 10 to the 20th power years or more, planets will either fall into their dead stars or be ejected into interstellar space. Even solid matter isn't eternal. Given enough time, quantum mechanical effects allow particles to tunnel through energy barriers they couldn't classically overcome. Atoms in white dwarfs and neutron stars will slowly fuse through quantum tunneling, eventually converting all matter into iron 56, the most stable nucleus. This process, called the iron star phase, will take at least 10 to the 1500th power years, a number so vast it defies comprehension. Black holes, those regions where gravity is so strong that not even light can escape, will dominate the far future universe. They grow by swallowing any matter that comes too close, and smaller black holes will merge into larger ones. Supermassive black holes at the centres of galaxies will become ultramassive, containing the mass of entire galaxy clusters. These monsters will be the last repositories of the matter that once formed stars and planets and living creatures. But even black holes aren't eternal. Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint for stellar mass black holes, far colder than the cosmic microwave background today. But as the universe expands and cools, eventually becoming colder than even the largest black holes, they will begin to evaporate. The process is extraordinarily slow. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely. The largest black holes, those with the mass of galaxies, will take even longer to evaporate, perhaps 10 to the 100th power years. As they shrink, they heat up, radiating faster and faster in their final moments. The last second of a black hole's life releases as much energy as it radiated in all the previous eons combined. A final flash of light in the darkness. When the last black hole evaporates, the universe will contain only elementary particles, photons, electrons, positrons, neutrinos, and perhaps other particles we haven't discovered yet. This is the heat death of the universe, the state of maximum entropy where no more work can be extracted from any system. The universe will be a cold, empty void with particles separated by distances many times larger than our observable universe today. Occasionally, very rarely, particles might meet and annihilate, producing a brief flash of photons. Even more rarely, quantum fluctuations might spontaneously decrease entropy in a small region, perhaps creating a brief pocket of order in the vast disorder. Some theories suggest that, given infinite time, quantum fluctuations could recreate anything, even entire universes. A fluctuation could spontaneously create a brain with memories of a life that never actually occurred. A Boltzmann brain floating in the void. Given enough time, 10 to the 56th power years perhaps, a fluctuation could recreate something like our entire observable universe, complete with stars and planets and life, though it would immediately begin dispersing back into maximum entropy. Other theories propose different endings. If protons decay, as some particle physics theories predict, all ordinary matter will eventually dissolve into lighter particles and radiation. The timescale for proton decay, if it occurs, is at least 10 to the 34th power years, far longer than the current age of the universe, but still finite. If protons do decay, white dwarfs and neutron stars will eventually evaporate, leaving only black holes and elementary particles. Dark energy, the mysterious force accelerating the universe's expansion, adds another layer of uncertainty. If dark energy remains constant, the universe will expand forever, growing colder and emptier. But if dark energy increases over time, it could lead to a big rip, where the expansion becomes so rapid that it tears apart galaxies, solar systems, planets, and eventually even atoms. This could happen in as little as 20 billion years, though most models suggest much longer timescales if it happens at all. Alternatively, dark energy might decrease or reverse, causing the universe to stop expanding and begin contracting. This would lead to a big crunch, the opposite of the Big Bang, where everything comes back together in a final singularity. The universe would heat up as it contracts, stars and galaxies merging, matter breaking down into elementary particles until everything returns to a state similar to the first moments after the Big Bang. Some theories propose this could trigger a new Big Bang, a big bounce that starts the cycle over again. The multiverse hypothesis suggests our universe might be one of countless universes, each with different physical constants and laws. In this view, universes might be born from black holes or quantum fluctuations, evolving and dying in an endless cosmic evolution. Universes better at producing black holes would create more offspring universes, a kind of cosmic natural selection. Our universe, fine-tuned for the existence of stars and life, might be the product of countless generations of cosmic evolution. String theory and other attempts at quantum gravity suggest even more exotic possibilities. Time itself might be emergent, not fundamental, arising from some deeper, timeless reality. The universe might be a hologram, with all the information contained in a lower dimensional boundary. Extra dimensions might be curled up at every point in space, too small to detect, but influencing the laws of physics we observe. The Big Bang might have been a collision between higher dimensional membranes in a space we can't directly perceive. Some physicists propose that information, not matter or energy, is the fundamental constituent of reality. In this view, the universe is essentially computational, processing information according to the laws of physics. Black holes become information processors, their event horizons encoding all the information that falls into them. The heat death of the universe becomes a state of maximum information entropy, where no more computation is possible. Consciousness adds another layer of mystery to the far future. If consciousness is purely physical, it will end when the last information processing systems cease to function. But if consciousness has some deeper connection to the fundamental nature of reality, as some interpretations of quantum mechanics suggest, it might persist in forms we can't imagine. Perhaps conscious beings in the far future will find ways to survive the heat death, encoding themselves in the quantum vacuum or escaping to other universes. The anthropic principle suggests we observe the universe's properties because they allow observers to exist. In a multiverse with varying physical laws, we necessarily find ourselves in a universe suitable for life. This might explain the apparent fine-tuning of physical constants. If they were different, we wouldn't be here to observe them. The far future might see intelligent life engineering new universes with desired properties, becoming cosmic creators themselves. Time itself becomes strange in the far future. With no events to mark its passage, no changes to measure, does time still exist? Einstein showed that time is relative, flowing at different rates depending on gravity and motion. In the empty universe of the far future, with no reference points and no observers, time might become meaningless. The The universe might enter a timeless state, eternal and unchanging, until perhaps a quantum fluctuation starts the whole process over again. Yet even in this vastness of time, stretching from the Big Bang to the heat death and perhaps beyond, we find ourselves here, now, in this precious moment. We are the universe becoming aware of itself, matter organized in such a way that it can contemplate its own existence. Every atom in your body was forged in the heart of a star. Every moment of your experience is the product of 13.8 billion years of cosmic evolution. You are not separate from the universe's story. You are the universe's story, being told right now, in this instant. As you drift towards sleep, consider the incredible journey we've taken tonight. From the first moment of time itself, through the birth of stars and galaxies, through the formation of our solar system and Earth, through the emergence and evolution of life, through the rise of consciousness and humanity, to this very moment, as you lie here listening, and then beyond into futures both near and impossibly distant, where the story of time continues in ways we can barely imagine. The story of time is your story, my story, everyone's story. We are all temporary patterns in the flow of matter and energy, brief flames of consciousness in the vast dark. But what beautiful patterns we are, what magnificent flames. In the few decades given to us, we love and learn, we create and discover, we tell stories that span billions of years. We are the universe's way of understanding itself, and through us, the cosmos achieves a kind of awareness, however fleeting. Time moves forward, always forward, carrying us from birth to death, from order to entropy, from Big Bang to heat death. But in our consciousness, we can move freely through time, remembering the past, imagining the future, telling stories that compress billions of years into hours. Tonight, you've travelled through all of time, from the first moment to the last, experiencing the entire history and future of the universe, from the comfort of your bed. And now, as sleep approaches, you can let go of time altogether. In dreams, past and future blend together, causality becomes fluid, and impossible things become real. Your sleeping brain will create its own universes tonight, with their own laws and logic. You'll experience adventures that never happened, meet people who don't exist, visit places that aren't real, and yet in the moment of dreaming, they'll seem as real as anything in waking life. Sleep is its own journey through time. Your brain will cycle through different stages, consolidating memories, processing emotions, solving problems below the threshold of consciousness. You'll dream 4 or 5 times tonight, though you'll probably only remember the last one, if any. Each dream is its own universe, created and destroyed in minutes, populated by characters drawn from memory and imagination. In dreams, you're both author and audience, creator and creation. As you sink deeper into comfort and relaxation, feeling the weight of your body against the bed, the softness of your pillow, the warmth of your blankets, know that you're part of something magnificent. You're a collection of atoms that have existed since the early universe, arranged temporarily in a pattern that can think and feel and wonder. You're a way for the cosmos to experience itself, to know beauty and love and meaning. You're a story the universe is telling, and tonight you've heard the larger story of which you're a part. The universe will continue its story long after we're gone, long after Earth is gone, long after the stars themselves are gone. But right now, in this moment, you exist. You're here. You're aware. You're part of the grand adventure of time and space and matter and consciousness. That's an incredible thing, a precious thing, a thing worth celebrating even as we drift off to sleep. So close your eyes now and let yourself float in the darkness that's not empty but full of potential. Every point in space seethes with quantum fluctuations, particles appearing and disappearing too quickly to detect. Dark matter flows around and through you, invisible and intangible, but shaping the universe with its gravity. Neutrinos from the sun, from distant supernova, from the Big Bang itself, pass through your body by the trillions without interacting. You're immersed in the cosmic microwave background, that ancient light from when atoms first formed, redshifted now to invisible wavelengths, but still filling all of space. You're never alone in the universe. You're connected to everything that has ever existed and everything that ever will exist. The atoms in your right hand might have come from a different star than the atoms in your left hand. The water in your body has been through countless cycles, raining from ancient skies, flowing in primordial rivers, locked in glaciers, drunk by dinosaurs, exhaled by plants. You're a temporary arrangement of ancient matter, a brief constellation of atoms that have been on an incredible journey and will continue journeying long after you're gone. But for now, for tonight, rest. Let the story of time fade into the background as sleep takes you. Dream your own dreams, create your own universes, experience your own adventures. Tomorrow, you'll wake and rejoin the flow of time, adding your own small chapter to the vast story. But tonight, just rest, carried by the gentle rhythm of your breathing, the beating of your heart, the slow processes of life that connect you to every living thing that has ever existed. The story of time goes on, will always go on, from the first moment to the last and perhaps beyond. But your part in the story, your conscious experience of it, can pause now in sleep. Let go of the vast scales of cosmic time and return to the human scale, the scale of heartbeats and breaths, of dreams and rest. You've travelled 13.8 billion years tonight. Now you can rest for 8 hours, gathering energy for tomorrow's journey. Sweet dreams, fellow traveller through time. May your sleep be peaceful and your dreams be wonderful. And remember, when you wake tomorrow, that you're part of the greatest story ever told. The story of time itself, still being written, still unfolding with countless chapters yet to come.